I am Francesco Marmo, and I will present a work entitled A Novel Approach to the Form Finding of Shells Based on Membrane Theory, authored by Stefano Gabriele from Roma University, Sigrid Adriaenssens from the Princeton University, Domenico Di Lieto, Massimo Paradiso Luciano Rosati, and myself from the University of Napoli, Federico II. I will first introduce the basic equation for membranes of arbitrary shape. I will present in more detail the horizontal equilibrium equation and the compatibility equation used to evaluate the unknown horizontal projected membrane forces. The height of the shell is then determined as a function of these projected forces and of applied loads. I will also present a numerical example regarding shells of assigned planform. Finally, I will verify my results by comparison with those obtained by the finite element method and a Relaxed-Funicularity. The membrane theory was developed by Pucher as a simplified theoretical model for the stress analysis of thin shells. This model neglects altogether bending and out-of-plane shear. It describes the equilibrium of curved shells by a set of differential equations in which the membrane internal forces are related to the height of the shell mid-surface. The shell height is represented by the function f of x and y. Membrane forces and loads are defined on this surface and are projected on the horizontal plane, that is, the shell planform, to obtain components nx and y and xy and q. This differential equation corresponds to the vertical equilibrium of a shell element. In this equation, the value of membrane forces is related to the height f of the shell. It can either be solved for the force components n or for the shell height function f. In this last case, this equation is easily used to finding the form of thin shells. However, it requires the definition of projected membrane force components. Projected membrane force components are required to satisfy the horizontal equilibrium equations and relevant boundary conditions. However, these equations are not sufficient to uniquely define the value of membrane forces. Analogy between these differential equations and those that describe plane stress problems is used to include an additional compatibility equation. In case boundary conditions are given in terms of displacement values at the shell support, this set of equations is recombined to obtain a different equation expressed as a function of horizontal displacements. Notice that the compatibility equations are obtained only from the analogy mentioned before. Thus, the assigned mechanical properties do not represent those of the actual shell. Neither the computed displacement represents the displacement of the actual shell. These sets of differential equations is solved by the finite difference method applied to a grid of nodes of arbitrary shape defined on the shell planform. To evaluate numerically the derivatives of all functions appearing in mentioned equations, a star of neighboring nodes is associated to each node of the mesh. Then, the Taylor series expansion of the generic function is written and applied to a pair of nodes pertaining to this star. This procedure produces an overdetermined set of algebraic equations that is solved by minimizing the residual b. This procedure is repeated for each differential equation or boundary condition listed in previous slide to obtain a set of algebraic equations that is solved for the values that the unknown functions assume at the nodes of the mesh. After assigning the shell planform and loads, the proposed form-finding algorithm employs the horizontal equilibrium equations to assign a compatible distribution of membrane forces. This specific problem is solved either by assigning thrust values on the entire boundary of the shell planform or by defining displacement values at the constrained portion of the planform boundary. The computed values on membrane forces are used into the vertical equilibrium equation to determine the shell heights. Once the shell height is determined, it is possible to update the projected load values and eventually iterate the sequence of operations until convergence. Finally, contravariant membrane forces can be computed on the shell mid-surface. This procedure is applied to a shell of assigned planform. The shell is supported at the corners where boundary conditions impose the value of displacements. At the nodes of the unsupported boundary and at the boundary of the central elliptic opening, boundary conditions are used to set null values of thrust. Solving the horizontal equilibrium and compatibility equations, the distribution of membrane forces is determined. Then the vertical equilibrium is employed to obtain the shell form. In this case, boundary conditions at the four corners are set in such a way to have different heights at the supports. Once the shell form is determined, it is possible to perform a finite element analysis of the shell with assigned geometry. Here is shown a comparison between the membrane forces computed from the proposed procedure and those computed from the FEM analysis. This comparison is possible also in terms of principal directions of the membrane force tensor. Both comparisons show very good agreement. The funicular efficiency of the form-found shell can be verified by computing the generalized von Mises value of the bending moment tensor, which is very low almost everywhere on the shell planform. An alternative approach consists in computing the minimum and maximum Cauchy stress components at the extrados and at the intrados of the shell. Here it is clear how tensile values are very low if compared with compressive ones. However, higher values of tensile stresses are computed for some regions of the shell mid-surface. Finally, here are proposed the results of a relaxed funicularity analysis of this shell. This contour plot shows how higher values of generalized eccentricity are determined within those regions where the minimum and maximum Cauchy stresses have been computed from the previous analysis. This analysis shows both the feasibility of the proposed form-finding procedures and the capability of the relaxed funicularity to highlight critical points of the distribution of bending moments within the form-found shell structure.